up guys? Today we're going to solve this question, shortest distance after road addition query part 1. So I'm gonna explain you with the example that as case 1 what this question wants us to explain. Let's say we are given a graph like this which is connected with a single edge and it is a what do we say a unidirectional graph. So it's gonna move towards one direction. There is no other way. I mean it is not bidirected graph which is connected to both ends. It's gonna move in single end. And also it is a acyclic graph so there is no kind of cycle present in the graph. So in the question they have given us the query of array in which we're going to iterate over it again and again. So from starting to ending. Once we iterate over this array, we found out that in the graph, we just added a new node. So what we're going to do, we're going to calculate the shortest distance between the starting position and the ending position of this graph. So once we start from 0, we found out that if we take 4 steps from 1, 2, 3, 4, we can reach to the end query, I mean end position of the node. But since in the question they're given the query which adds another edge over this graph, which makes it more shorter. So the shortest distance, as you can see, since we can skip 3, so it's gonna be 3. Then after that we iterate over this part. So they just, after we're done with this, we're gonna iterate over this query. So in this query they just added a new node, I mean new edge, which is from 0 to 2. So since it is from 0 to 2, and if we just simply observe that the shortest distance is basically 2, I mean this one and this one's the shortest distance is 2, so we just need to put 2 over here. We're going to make a resultant array. Now in the end they just given us the direct shortest path, which is kind of displacement in my terms, but anyways, yeah. So in the end they just gave us this connected edge which is from 0 to 4, and I can simply see that there is only one step needed to reach to the end destination. So I'm gonna put one over here. So this is what the question wants from us. So I mean, how can we do this? Yeah, so since it is graph question, we're probably going to use a DFS or a BFS, but I think that breadth first search is kind of optimal solution for this, and I'm going to explain you that how to implement the breadth first search. I mean, yeah, that's it. So let me just show you how to do it. I mean, what is the approach behind it? So since I've shown you that our main approach is just to go from the source to destination, that's our main approach, and that's it. That's all what we need to consider. So let's say we have done a breadth first search. So in the breadth first search, we're gonna use adjacency list. So what is an adjacency list? Adjacency is nothing, guys, but let's say I'm at this position 0. I'm gonna create an array in which I'm gonna tell this 0 can go to which place. This can go to 1. But there is a special case about 2. 2 can go to 2 places, which could be 3 or it could be 4. So we're simply going to iterate over it. So in the first case, since we had 0, we're gonna, let's say 0, which like I said, we're gonna start with 0. So let's say I've maintained a queue in which I'm starting with 0 and current length of the path is 0. So what I'm gonna do next, the 0th next neighbor, as in breadth first search, we're going to look towards the sibling. So next neighbor is 1. So I'm gonna add the 1 into my sibling. Since I've added 1, the path will also increment by 1. Then after that, I'm gonna reach to 2, and if I reach to 2, which means the path is 2. But here is the case, once I've reached 2, I can see that the 2 have 2 neighbors. I mean it can reach to 3 and it can reach to 4. But so it would be kind of like this. We can reach to 3 and the path will become 3, and we can also reach 4 since it have 2 neighbors. It can go to 3. So as you can see, our algorithm will stop at this point. Why at this point? Since 4 is the end value, I mean end node, and we know that the length of it is 5. So basically how are we going to calculate the 4? I mean if we subtract the length minus 1, its value is always equivalent to the end node, which is 4. So that's why we got to know that we need to stop over here. Since we stop over here, since we got the end node, we gonna pick that, check that, okay, this one is the shortest value. How did we do that? Simply, man, I mean we simply reach the edge case. Although it's not gonna move forward and gonna check that what 3 neighbor is. 3 neighbor is obviously going to be I mean it's gonna be 4 and the length become 4. But before doing even that, we gonna put a condition in which we gonna check that the current index is kind of 4. So we have reached our destination, and this is going to be the shortest path. So I'm gonna just show you to the code so it will make it more easier and more clear. So let's just consider right now that I have an adjacency list. So for the adjacency list, I'm not going to use a map since the array, I mean the graph which we have is already in order. So we are assume that the 0th index will have this, 0th index will have this array, and the first index, I mean you know array how it works. So yeah, that's why 0 is connected to 1 and it is official, which is shown right over in that place. So I'm gonna move it over the n so that it gonna create some kind of array like this. I'm gonna just show you a small starting position of like this. So the 0th index from the 0 net node can go to 1, then first node can go to 2, and so on. And you must be thinking that what if we reach to 4, 4 reaches 5? I mean yeah, it's technically, I mean wrong, but it doesn't affect anything since we're gonna stop at this position anyway. So it is kind of null. So that's the whole thing. That's the main motive behind the adjacency list. Then what we're gonna do, we're gonna create an what do we say, resultant, and according to the quotient we're gonna iterate over each query, which is gonna give us the source and destination in what do we say queries. Then after that, what we're gonna do, we're simply going to reserve, I mean we're gonna agency, I mean we're gonna increase the possibilities of nodes. I mean by that, I mean basically means that let's say I'm source over there. I'm gonna increase the neighbor of it. Since this query increases the neighbor of a particular edge, let's say the simple thing, you can simply just see over here. It was, the its neighbor, 2's neighbor was 3, but since the query is run over that place, so we're just going to append 4 into the list. So that's what we're gonna do. That's how we're gonna create the edge list. So that's why I'm doing this right over here. Since we do that, we're simply going to append the breadth first search value, whatever the value comes out to be. I'm gonna just write the code for the breadth first search, and in the end I'm gonna return the array. So what we're gonna do in the breadth first search, like I've shown you in the breadth first search, we use a queue just to visit the neighbors. So let's say we initialize a queue. In Python we have already a queue, so we're simply going to use this dequeue. Then after that, like I said, we're gonna feed this queue with the initial value 0 and 0. So basically the first one means that it is a node, and the second one basically tells the length of the path. Then after that, what we're gonna do, we're gonna maintain a visit, no I mean visit set, so that we don't get to that same place again and again. So it will just reduce the computation, and it will increase the optimize it, what do we say, increase the speed, make it the code more optimized. So then after that, we're gonna add 0 since we have used the 0. What we're gonna do, we're gonna create a loop, and this loop will iterate until the queue is empty or we have reached a satisfied condition. So let's say current position and the length which we have would be in the pop left side of the queue. So we try to pop it out. Once we pop it out, we're going to check if this current node is equal to n minus 1. If it does, then we congratulations, we have reached the end of the queue. If it doesn't, what we're going to do, we're going to iterate over the neighbor of it. How are we going to do? In the adjacency list, we know that the index depict this index, the current index, will gonna give us an array of neighbors. So we can iterate over the array of neighbors. So if neighbor not in visit, if it is not visited, what we're gonna do, I'm gonna tell that okay, if it is not visited, we're simply going to append it to the queue. In the end, I'm gonna say enable like this. Since we have increment one more time, we just move one step, so we're gonna say +1 since it is a one step. Then after that, I'm gonna just say visit dot add this neighbor, since we have used this neighbor and we don't want to use it again. So that's a pretty much code. Hopefully let's see if it does work or not. Let me just run it. mm, and let's see if this thing will work. Yeah, so that's how we do it. That was pretty much it. Thank you.